Hello again. This video is going to be a worked example of a fairly standard 2D motion question. A boat traveling across a river at a certain in direction with a certain current going on. We have right angles here, so the mathematics is fairly straightforward, but there is an interesting aspect at the end, working out the direction, which will test your understanding of the sine function. But this is a good thing, a good exercise for all of you to study. This is a type of question that is fair game for grade 12 physics students as well as grade 11 TOPS physics students. So hopefully this worked example will make it easier for you to understand. Okay, so here's a basic type of navigation question you might get. A boat crossing a river, fairly straightforward question. The boat is going to travel from location B to location A. Sometimes in these questions, teachers will put the names of towns or whatever. We won't bother with that. Location A is due west of location B. Our river is 4 kilometers wide. The boat engine can put us at 15 kilometers an hour speed across the water in any direction. The current is currently going 4 kilometers an hour due north. So if we imagine this, the travel then is going to be this direction. The river's traveling in this direction. So we have a right angle. The question then, which I didn't write down, but I can verbally say, is what direction should the boat captain steer the boat so that the boat will ultimately go straight across the river? In the last slide, if you steer the boat straight across the river, the current is going to push you north, and you will end up further downstream than intended. If you are too aggressive with this, it will turn you the other way, and you will go upstream in an unintended way. So what we want to do is find the optimum direction to tell our captain, assuming the current and everything stays the same, to steer the boat. The second part of the question will be, well, how long then, given that, will this trip actually take? So the first thing in my algorithm was to look at converting units. So you have, given here, 4 kilometers wide river. So we convert that to 4,000 meters, and you then have to be very careful that you've got your SI prefixes well understood so you don't make silly mistakes. At this level, that's not good enough. The speed of the boat, notice these aren't vectors, these are just the magnitudes. 15 kilometers an hour divided by 3.6 is 4.17 meters per second. You might say, well, how do you know it divided by 3.6? Well, a simple calculation will show you if you walk at 1 meter per second, you're going to go 3,600 meters in an hour. So therefore, 1 meter per second equals 3.6 kilometers an hour. That gives you the relationship you're looking for. So meters per second should always be smaller than kilometers an hour. That way you know you're going in the right direction. Finally, the river, 4 kilometers an hour, divided by 3.6 gives us 1.1 meters per second. So we have the values that we need now properly converted so we don't make silly mistakes. The next step is to reconcile our angles. We are given or inferred compass bearings. So the ground track is the path that we tend to follow, which is directly from B to A. That is due west. So due west in the compass bearing world is 270 degrees. But in the theta xy world, you're simply going around like so. So this is 180 degrees. You can also, of course, use the 450 minus 270 to get 180 if you want. But thinking about these questions a little bit and getting some situational awareness will really help you to catch mistakes. The river's direction is due north, which in the compass world is 0 degrees, and in XY world is, of course, 90. The direction that the captain is to steer the boat, of course, is unknown. That's what we're trying to solve. And so if the compass direction is unknown, then clearly the XY direction will also be unknown. And we have to leave it unknown for now. Third step was to obtain our vector triangle. So you can see here, this is where we start. We're going to go straight across following this ground track, so that this VGT will be our velocity going straight across. This magnitude will be less than the 15, or 4.17, because some of it is being used to offset the river. Okay? And so as a consequence, the direction is known, but the magnitude of this one is not known. The river, we understand completely, as you will see in the next slide, and the direction that the captain must steer the boat. We know how fast we go in this direction, 15 kilometers an hour, but we don't know what direction to steer the boat. Remember that graphically speaking, vectors must be added head to tail. We said that the VGT vector is always the sum, it is always the resultant. So in that case, we have to be very careful with the vectors, that we can always put the river one on there as well, but we have to be sure that the head to tail thing works so that this plus this equals this one. And drawing these triangles is doesn't take very long, and is a real help for you if you understand the question. If this is done improperly, it usually leads to troubles later on. From the triangle, we can easily get the vector equation. Okay, VR plus VB equals VGT, which is exactly what we have here. And you can always check this, because your VGT vector, your ground track, must be the resultant, because it is what we observe. When we watch the boat, we sit on the shore and watch that boat go from A to B, all we see is the boat going from A to B. All this other stuff is hidden underneath. Okay? Which is why we make this calculation. Now I'll move on to the next panel to do the components and so on. Hopefully you're able to follow along. Okay, so step 5 then is to compute the components, the XY components of the 3 vectors. So once again, remember that you have not 2 but 3 vectors here. You have the ground track, the river's velocity, and the velocity of the boat with respect to the water. So we already know what to do. We've been talking about this before. We take components the way that we always do. These, when I take the vector hat off of VGT, this implies the magnitude. In mathematics, sometimes they'll use what appear to be absolute value signs. In physics, it's more customary just to remove the vector hat to keep the symbolism a little bit cleaner. So once again, it's magnitude times the cosine of the angle. In this particular case, the magnitude is unknown. We don't know how fast we're actually going to travel from B to A across the water yet. And the angle is 180 degrees. So the cosine of that is -1. So we get, in the end, negative VGT. And we have to be comfortable leaving some of these values unknown and leaving our algebra as it is. VGTY is simpler. The sine of 180 is, of course, 0. So this becomes 0. The river is completely determined. It's going straight north. So we fully expect, if we go back to this one for a minute, the boat is going from directly west. There is no motion in the north-south direction. As a consequence, we expect this to be 0. So if you understand the vector triangle in the previous slide, you'll be looking to see that these things make sense. Even this one, the fact that it's traveling this direction, would imply that the value we get is negative. So the river then, in the same vein, going due north, we expect no x motion, so that's going to give us 0, and the y motion will be fully the speed here. And we now put the explicit algebraic sign to imply that it's a one-directional vector. And then finally, this mysterious one, what the captain is supposed to do. Well, we have the magnitude, the 15 kilometers an hour converted to meters per second here, but we don't know the angle, so we have to leave this unevaluated. That gives us the 6 numbers. Remind ourselves of the vector equation, which tells us what to do. But now we have to do this equation twice, one in x and one in y. The x version then, we just take the numbers we've computed, VGT, 0, and 4.17 cos theta b. That's one equation. Another equation is y, in the y world, is going to be 0 plus 1.1, or equals 1.11 plus this expression. Now if you look at this, you're going to see, of course, the first one has 2 unknowns, and you really can't do much with that. But the second one is going to give us an easy solution. We have a number, a 0, and a multiplier, a coefficient, and we can quickly solve using basic algebra to get sine theta b is equal to negative 0.27. Now we've got some thinking to do with this answer. It's not completely clear. You can't just type it in your calculator. So the next slide we'll talk about how we reconcile this angle and decide exactly what to tell the captain. Now this slide is pretty important for understanding the solution to this question. This is where a lot of young people have some trouble. You've done the algorithm, and what's happening now is some of your basic mathematics is letting you down. You're used to just typing numbers in your calculator and getting the answer. And that's because you generally live in a world that is between 0 and 90 degrees. However, the world is generally not that kind. And so when we get beyond 90 degrees, we have to put our thinking caps on. Now what you've done already so far will tell you what to do. But it is your awareness of this that is really important. So let's have a look. If we look at our vector triangle here, we're going from A to B, and VGT is straight across, the river is going straight north, and the boat has to angle its direction slightly upstream to offset the river current. Now most people, if you explain that to them once or twice, will get it. But the problem is taking the conceptual idea and converting it into a knowledge of what to do with the calculation. In other words, this literacy that comes from this. Let's see if we can figure it out. If we look at this vector here, we can see that it has first quadrant, second quadrant, and now it's clearly in the third quadrant. Okay? Just from your basic geometry, you know you're in quadrant 3, and you've been taught quadrant 3 is in the angular range from 180 degrees to 270 degrees. And we'll draw, just for fun here, a little diagram up here to remind you. 1, 2, 3, and 4. So at something over 180 degrees, we're in this area. Our VB thing is pointing in that direction somehow. So we have to make sure that when we finish this, that we get an angle that is in the right quadrant and that is valid for this question. We've been given in this calculation that the sine of theta b is negative 0.27. When you enter that into your calculator, you get the answer of negative 15.7 degrees. But that's not something that you can tell the captain, steer negative 15.7 degrees. Because what is negative 15.7 degrees here? It's this direction. They'd be running the boat into the land. That's nonsense, right? So, let's understand a little bit about what's happening. If we draw a sketch here of the sine function, you will see, and remember when we do inverse functions, when we take the arc sine here, we are starting with an argument on the y-axis, going over to the graph, and our answer is on the x. Normally we start with the x and get our answer on the y. Inverse functions work in the opposite direction. So what happens is if we take negative 0.27 here, move across, hit the curve, come down to the axis, we get this negative 15.7 degrees. But it's in the wrong quadrant. So we look at our sine function here. We know we have to be between 180 and 270. Here's the 270. So we have to have an answer that's in between here. Does the curve exist between these two? Yes, it does. So what we can do is take the negative 0.27 and just sketch it along here till we hit our curve. And then we're going to come down to the x-axis. And what you'll find is the difference between 180 and the point it comes down will be the same. It'll be this 15.7 because the sine function is symmetrical. However, you'll also realize that we have to add 180 because we have 15.7 here plus the 180 from here to here. Okay? So 15.7 plus 180 gives us 196. But remember, that is still theta b. That's not what we tell our captain. We have to still make another conversion. So gamma b, which is what we do need to tell the captain, is going to be simply 450 minus the theta b. So 450 minus 196 gives us 254 degrees, and that's the direction you tell the captain to steer. Now we can all check this just to see if we've goofed it somehow. The 196 is an angle that is slightly past 180. That looks like it's going in the right direction. If we look at our conversion and we say, okay, well now 254 degrees, so if I come around my compass, 180, if I go this far it's 270, no, I'm short of it. Ah, yeah, okay, that looks pretty good as well. And so we have taken our knowledge from the vector triangle here, knowing that it's in quadrant 3 in this particular example. It won't always be, of course. And then inspecting the sine function to understand it a little bit better, to take from this our answer. So here's a case where we have the 3 steps of constraint theory. Fundamental constraint of the question, which in this case is the definition of the ground track. Technical definitions are going to be your vector equations, your taking of components, and things like that. But in this particular example, what can let young people down is the actual third thing, the algebra, the thing you're supposed to be good at. And it's largely because a lot of times students have a little bit of trouble understanding what's going on with these functions and what the calculator tells you and what the correct answer really is. And this is different than a tan function, which is consistently 180 either way. This one's symmetrical, so you have to deal with it in a different way. And it is done by simply looking at the graph and inspecting and understanding what an inverse is. Starting on the y, moving across to the appropriate part of the graph, and coming down to the axis and finding your answer there. So final panel then for this question will be finding how fast we're traveling across the water to from A to B, and then thus how long this trip would take. So this is the last little bit of this question where we deal with how long the trip would actually take to go across the river. Now remember that our speed along the ground track is not going to be the speed of the boat, because we're giving some of that up to fight the current. So to think that VGT is the 4.17 number without any kind of change shows that you're not there yet in the sense of your understanding. So we have again the same equations we had in the last slide, the equation for the x components and the equation for the y. In the last one we solved for theta b and we obtained a value of 196 degrees. So we can substitute the 196 into this equation, which will now give us an explicit answer for VGT. So you can see, we put it in, we get negative 4.01, and there's a negative here as well, and this comes out to a positive. Now remember, because this is a magnitude, it should always be positive. There's no plus sign because this is a scalar. But the point here is that the magnitude here has to be always positive. So when you do your calculations and you get a negative number here, you're missing something, okay? Remember how we set up the question, VGT cos, VGT sine, and VGT is therefore a magnitude. It is not a vector. So we end up with this thing, 401 meters per second. The time to follow the ground track will be the distance of the ground track, which is 4,000 meters, divided by the speed along the ground track, which is 4.01. Straight arithmetic comes up to 998 seconds. But this number is not useful. Most people, this number doesn't mean anything. And out of respect to the question, you are to convert it to a more useful day-to-day unit. In this example, 16 minutes and 36 seconds. Now you have the full solution, okay? The direction in the previous frame of which way to point the boat, and here's a question of how long the trip will take. Now I know this was a little laborious and we have a number of pains to look through this, but you do see now how we can calculate the direction, how we can deal with the subtleties of how we obtain the inverse sine function and how it can mislead us initially if we're not careful, and it's a little bit more complicated than the arctan function is. So there's some instruction at the end of this that you really do need to pay attention to, and that's really been helpful, I hope. Now this is gives you a pretty good idea. And again, for grade 11 tops, grade 12 of the regular university stream physics here in Ontario, that would be a question that you could be reasonably expected to answer. So hopefully this clears it up. And again, on my final slide is the contact information if you're having any difficulties. Thank you again for watching.